We are in business. All right. So
Round of applause for
after,
everyone.
yes,
Teamwork.
no, you guys were the brains. I just followed directions. So I'm really really glad that this was able to work.
Yeah, I would just double check what Joe said in the chat. Like he said to check to make sure the recording is also recording your iPad screen sharing and not just your profile picture.
uh, let's see that.
I was muted. I guess there's no real way to really know that until the end
Yeah,
of this lecture, but the worst that would happen is there's one lecture without recording and, small sacrifice in the way of moving.
Better the beginning than like halfway through the course and it's the super advanced stuff.
Yeah, better than when you're going over convolution. Yeah.
you guys got it. Uh, okay, so what I'm doing is I'm trying to use another software to record. So we have two copies. Let's see. Okay, so now we are recording on two devices at the same time. So if one of them bugs out, we have the other one. All right, let's start talking about things that matter. Um, the size of the signal. So we were talking about signal classification. We talked about how to find the energy of the signal. And we looked at one example in the previous lecture where we had 0, and then for some time the signal was 2, and then for some other time the signal was 2 e to the negative t over 2. All we did was we expressed that in bracket notation. Then we found the energy of that signal by using that particular formula, which essentially means that no matter what you have for f, whether it be a real valued signal or a complex valued signal, you can do a magnitude squared of that signal and then you integrate over all time to find the energy. You can also think of it as applying a limit where t can be extended on either side to infinity. So we took that example and then we found 8 units as the energy for that particular signal. Uh, and then we moved into the conversation of the power of the signal, which is essentially the average energy of effort t over a period of time. So one thing to note, and you guys have been talking about that, is that the power for a periodic signal, like the one that is shown over here, for periodic signal, the power is essentially the power of one period, because after that it is just the repetitive of the same one of one period. But in a general case, what you would do is you would find the energy of the signal and you would divide it but by all the time for which the signal was non-zero. We went over this particular example earlier where we had a sawtooth waveform where it was linearly increasing with a slope of 1 from negative t to t, where we set this to negative 1 and plus 1. We found the power by applying that particular formula to be 1/3. Essentially, that's where we stopped. Now we are going to move to the classification itself, energy versus power signals. So for energy signal, we can call it an energy signal if the energy of that signal is less than plus infinity, which essentially means that it is finite. So if the energy of the signal is finite, then we would call it an energy signal. Now the related question is, what is the power of an energy signal? We know the formula of that of to compute the power of the signal. And we know that for this signal, the energy is finite. So that means that this particular term is going to be finite. So we are taking something finite and then dividing it by cap t, which has a limit t tends to infinity. So you got a finite number divided by something that tends to infinity. Your power is essentially going to tend to 0. So the power of an energy signal is then 0. Next, power signal. How do we classify a power signal? F of t is a power signal if its power is between 0 and infinity. Next relevant question, what is the energy of a power signal? We will do something very similar to what we did over here. We will trying to find the energy of that signal by applying the limit t tends to infinity, negative t to t, absolute of f of t squared dt. Now we'll play a little trick over here by, multiplying and dividing by 2t so that we have this particular term representative of the power of the signal. In this case, we are saying that it is going to be between 0 and infinity. So you take something that is between 0 and infinity and you are now multiplying with 2t. Again, t tends to infinity, so that product is essentially going to be infinite. So the energy of a power signal, the answer to that is that it is infinite. Now, based on these two, I hope you guys can see that we can make these two statements over here. We said first, the energy signal f of t is energy signal if EF is less than infinity, and it is a power signal if the power of that signal lies between 0 and infinity. So which means if you look at both of these statements at once, a signal cannot be a power signal and an energy signal at the same time, because what we just derived was that if energy is less than infinity, the power of that signal will be 0, and this, if it's a power signal, we said EF, energy of that signal, is infinity. So if you combine those two statements, you know that the signal cannot be both power and energy at the same time. The units of these are right now we could be looking at milliwatts, we could be looking at watts, we could be looking at dB. Right now we are looking at just power units or energy units. Let's see, the next point is, there is however a possibility that a signal is neither a power signal nor an energy signal. So that's a possibility that we need to be considering. Example, when the function is literally t, so something that is increasing with a slope of 1 from negative infinity to infinity. There are no limits over here. So if you have a f of t equals t, it is actually a signal that you cannot classify as a energy or a power signal. Let's actually kind of quickly prove that. So let's try to find out the energy of this signal, which is t. So EF is negative infinity to infinity. You got magnitude of f of t squared dt. In this case, f of t is simply t. So you would get infinity, infinity. It's a real valued signal. So you got what? T squared will be t cubed divided by 3 with definite limits negative infinity to infinity. Over here, you have what? Infinity. How about the power? You got limit t tends to infinity 1 over 2t applying that formula. Limit t tends to infinity 1 over 2t, and then we've got t cubed divided by 3 with limits negative t to t, which means it is limit t tends to infinity 1 over 2t. Over here we've got 2t cubed divided by 3, which means when you simplify it a little bit, you get t tends to infinity. 2 cancels out, t cancels out, so you got t squared divided by 3. And you apply the limit now, you get infinity. So based on that, you can say energy is infinite, so it's not an energy signal. and power is infinite, so it's not a powered signal as well. So I hope that was helpful with how to go about finding out whether a signal is energy signal or a power signal or neither. All right, let's move on quickly to our next lecture, which is going to be on common signals. So we looked at a few common signals earlier. We looked at a unit step, then we looked at a constant signal. We talked a little bit about a sinusoidal function. So we looked at a few. We will add to that list today by looking at the ramp function, denoted as R of t. All it does is it is going to be 0 for time that is less than 0, indicated by the bracket notation over here. And R of t will be t for time that is greater than or equal to 0. So simply something that goes up as time increases with a slope of 1. So at 1 it is 1, at 2 it is 2, and so on. So that's your common signal R of t. Now, a related sketch is drawn at the bottom of the screen where you have another signal that is increasing with time. So it's also a ramp, but it is not R of t. It is similar to R of t. Over here, the slope is different. As you can see, dy is 1, dx is 2. So the slope is actually half. So even though my x-axis is time, my y-axis is not R of t. It should be half of R of t. And the reason is the slope is now half. So it's half of t. So let me copy this bracket notation and adjust it a little bit to complete the bracket notation of our new ramp signal. And I will make modifications to this in red. So now I don't have R of t, I have half R of t. And I don't have t, I have t over 2 for time greater than or equal to 0. And it is 0 for time less than 0. So that's fine. Now, can we go from one kind of signal to the other? The answer is yes. So over here, we are looking at two sketches. On the left, you have the unit step. So something that is 0 for time less than 0. And at time 0, it steps up to 1. And then it stays 1 for the remainder of the time. That's on the left, the unit step. On the right, you have the ramp, increasing with a slope of 1, R of t. Now, how do I go from u of t to the other? Well, you can clearly see that as you are increasing time, all you're doing is accumulating more and more area. And the area is increasing linearly, and it is increasing linearly with a slope of 1. And you can make all those statements by looking at the area at 1, by looking at the area at 2, and so on. And you will see that the area is actually 1 and 2 and 2, 3, and so on. So you can make all those deductions. So all you're doing is you're integrating u of t to get R of t. And the exact integral can be expressed in this way. R of t, which is the ramp signal on the right, is essentially integrating u of tau. I'm using tau and d tau because I'm using t, because my answer should be in terms of t. So let me highlight this. This is done so that I get a t there, and this is done because I'm integrating with respect to tau over there. So I'm using two time variables. One is my integration variable, and then the other is my integration limit variable. So as I integrate from negative infinity to infinity, essentially I'm scanning all the way from the left here. I accumulate no area as time is less than 0. But as soon as I get into the positive time here, I will accumulate area linearly, which goes up with a slope of 1. So that's how you can take a unit step, integrate it to be able to express as a ramp function. So there's a question on the chat box. For the second ramp function, shouldn't we have t over 2 but not half of r of t? They are both the same. So in this case, you see, what would I write over here? So let's say I say this is some x of t. Can I write it? Can I express it in the form of r of t? Well, all I have to do to r of t to be able to express it in terms of x of t is simply divide it by 2. So I'm saying x of t here is going to be half of t. So even though I do this, it doesn't really matter, right? Because it's going to be a 0 anyway. Yes, it is half of the original r of t. Yes. So I'm using r of t, sorry, I'm using r of t to indicate here and here. All right, let's move on. We looked at the integration of u of t to get r of t. Let's keep moving. Before I forget, I would like to point out one thing about complex numbers so it's kind of a tangent that I'm going on, but I wanted to do this at the beginning of the lecture, but because I got distracted with all the technical details, I want to address it right now before I forget. So for complex numbers, you guys are, you have the background. Most of you have the background, and if not, there is a set of notes provided by Professor Tajer. With his permission, I have made it available to you, so you can read through them. There's a 5-page document, but there is one thing that is I've seen many students kind of uh, make this mistake. Professor Tajer, yes. So I've seen many students make this mistake, which is why I'm going to address it right now, which is about the phase of complex numbers and how it depends on the quadrant the complex numbers lies in. So if you think about this in terms of quadrants, right? So on the x-axis and y-axis, I have real part of the complex number z and the imaginary part of the complex number z on the y-axis. So if your complex number is in the first quadrant or the fourth quadrant, then when you use a calculator, you will get the correct answer for the phase. You do the tan inverse. So if the complex number z is a plus jb, you will do tan inverse of b divided by a, and then you will find the phase. However, what would happen if the complex numbers lies in the second or the third quadrant? I hope you see that both b and a can be positive or negative, which means if one of them is negative or both of them are negative, what would happen? So for example, in the first quadrant, right, both of them are positive. So you get a tan inverse of a positive number and you would get the phi correctly, fine. It is still okay if the number is in the fourth quadrant. You will get a tan inverse. In the argument, you will have a negative number, which is fine. But what about over here? The real part is negative, the imaginary part is positive, so you will have to add pi to your answer or subtract pi to your answer. Your calculator is not going to tell you that. The calculator is actually going to give you this answer because you just insert the numbers. So I want you to think of it in terms of which quadrant the number lies in. So if it's in the third quadrant, then find phi, and essentially you would have to add 180 to get to that third quadrant, because you will get the answer as plus 35, but you would have to actually get it between 180 and 270. So you'd have to add that pi or minus pi. This way, you can come to it this way, or you can come to it that way. So instead of thinking about it mechanically and plugging complex numbers into the calculator, I would recommend you to first think about which quadrant the number lies in, and then adjust that angle by adding and subtracting pi. Adding or subtracting pi. Q3 and Q4. Right. So here, this is quadrant 3, right? So if suppose that your complex number is quadrant 3, it belongs to quadrant 3, which means that both the real part and the imaginary part are negative. A is negative, B is negative, right? The complex number is A plus JB, both A and B are negative. So what would you do? You would find in your calculator tan inverse B by A. So you would get something that is over here, but you would have to add 180 to it or subtract 180 to it. Both ways you will end up at the same spot, plus or minus pi. You guys see it? And then similarly, the same thing would apply for quadrant 2. So if you are in quadrant 2, use the numbers in quadrant as if they were in quadrant 4 and adjust it by pi. So this is documented in the write-up as well at the very end. But I want you guys to be thinking about the quadrant of the complex numbers as well, which is a very common mistake, which is why I thought I would point it out. Everything else is sort of mechanical, and calculators are there to help you along. Okay, that's as far as complex numbers, what I wanted to point out. Next, let us talk about the complex signal, the sinusoidal function. So you have seen this several times. Let's give it a quick look over here. The function f of t is described as a sinusoidal function over here. It is represented as a cosine 2 pi f0, which is the fundamental period, t, it's a function of time, plus some phase theta, plus b. And time over here is going from negative infinity to infinity. So it's defined as a sinusoidal periodic function that goes on forever. Now, just to describe what A and F0 and theta and B are, let's describe them over here. A is the peak amplitude. Well, I should also point out that I'm sort of ignoring the offset over here when I say that. Because if you take a look at, if you include the offset B in this, then the peak amplitude will be A plus B. But just as far as the definition of A is concerned, it is the peak amplitude as long as I'm ignoring the offset. 2A is going to be the peak-to-peak amplitude of that sinusoidal function. F0 is the frequency or the fundamental frequency in hertz or per second. Omega naught is 2 pi multiplied by the frequency F0 expressed as radians per second. Or it's also called radian frequency, and then frequency here. T0 is the time period, or simply the period in seconds. You compute that by doing a reciprocal of frequency. Theta can be expressed in radians or in degrees, and it is the phase of this sinusoid, essentially telling you where that sinusoid begins. B is the DC offset, which is directly related to the average of this signal. So to get a better understanding of all these parameters of this sinusoidal function, I've sketched up one arbitrary sinusoid here. This is 3 plus 2 cosine 4 pi t plus pi over 2. That's the function that I've sketched out. The time period, as you can see, let's say that is going to be the time period here, which is of half a second. So that's how you get that. Then you invert it to get f0, which is 2 hertz. 2 pi f0 t is going to be what? 4 pi t, because f0 is 2. So the radian frequency omega naught will work out to be 4 pi radians per second. The offset over here, or the average of this signal, is going to be 3, as you can see over here. So if you were asked to find out the average of the signal, it would be 3 for this guy. All right, so some parameters over there, and you can clearly see that we have adjusted the phase by pi over 2 degrees, so it has moved a little bit. Let's move on here. Another common signal is the real exponential signal. Later on, we will look at the complex exponential signals as well. Over here, f of t is expressed as a e to the alpha t. Both alpha and t are in the exponent. T is going from negative infinity to infinity. Alpha and a, those parameters belong to the set of real numbers. So that's why we are considering this as a real exponential signal. Now, if alpha changes, what would this function look like? So at the bottom figure over here, we are sketching a few things. One is when alpha is greater than 0. So for example, 1, 2, 3, and so on, you get e to the 2t, 4t, 5t, and so on. What do you have? You have a growing exponential. The choice of the color indicates that we should be worried about this. Why? Because something that grows exponentially with time can be indicative of instability, an unstable system. So that's why I've indicated that as growing exponential in a red color. That's when alpha is greater than 0. For some arbitrary real a. In this case, a is positive. When alpha is less than 0, that indicate, and if you sketched it for time going from negative infinity to infinity, in this case I'm only sketching from negative 1 to 1, that real exponential will be a decaying exponential. The green color is chosen because in most systems, when that decaying exponential is observed, it is indicative of stable behavior, good things happening. Now, when alpha is 0, f of t is simply a. So that's what your line is, a. So a is some constant over here which is positive. If a is negative, then everything will be flipped about the horizontal axis. So that's as far as real exponential signals go. A and alpha both real in this case. Next, we are going to talk about complex exponential signals here. Same function, a e to the alpha t. However, t still goes from negative infinity to infinity. However, a and alpha belong to the set of complex numbers. So we'll represent a as r e to the j theta, a complex number expressed in polar form. Alpha as a plus jb, a complex number in Cartesian form. You can clearly see, we can write down a few things, right? We can say a equals real part of alpha, b equals imaginary part of alpha, and we can also say r cosine theta is, let me do it this way, real part of a is r cosine theta, and imaginary part of a is r sine theta. So I'm just simply using Euler's identities to express real and imaginary parts of these two complex numbers, alpha and a. One is in Cartesian form and the other is in polar form. Okay, now let's see what f of t works out to be. F of t is a e to the alpha t. We can substitute for a. because we have defined it. We can substitute for alpha because we have defined it. What do we have? We have A as r e to the j theta, and e to the alpha, sorry, let's use it, e to the alpha t as e to the a plus jb of theta. We can simplify a little bit by combining the exponentials which have a real exponent and a complex exponent. So we are combining the e to the j terms over here in blue, and the remaining terms are over here. R is outside, e to the at is also outside. Next, using Euler's identity, we can express e to the jx as cosine x plus j sine x. R e to the at remains as is. So now we have a complex function f of t, which we can individually separate as real part of f of t and imaginary part of f of t. The real part of f of t is going to be what? R e to the at cosine theta plus bt. So all of that is the real part of f of t. And imaginary part of f of t is what? R e to the at sine theta plus bt. Written up over here. Real and imaginary parts of this function, they are both exponential signals which have a sinusoid aspect to it. So these are sinusoids that have a exponential envelope. So they are either decaying or growing exponentials, but that exponentials is the behavior of the envelope, the overall signal. Inside that, there is a high frequency, or there is a repetitive part, the cosine part, a sinusoidal part. Let's take a look at them by drawing a sketch. So I'm looking at these two functions. One, they could be decaying or growing depending on what a is, because this could be become really big, or this could be a damped sinusoid as well. So let's take a look at them by looking at a sketch. So same functions, and because they are just differing by the function cosine versus sine, we can look at them on the same graph. There is just a difference in the phase. Now, when alpha is less than 0, we had that real part or the imaginary part as r e to the at cosine or sine, and then you had the theta plus bt. So this guy, if alpha is less than 0, e to the negative 2t, e to the negative 5t, the envelope of this signal will be decaying, hence a decaying sinusoid. But you can also see that because of this cosine function, we have that sinusoidal aspect to that decaying sinusoid. So by looking at the parameters inside the cosine, we can find out what is the time period, frequency, omega naught of that particular sinusoid that is in green. But the envelope itself is doing a sort of exponential behavior. Same thing is true for when alpha is greater than 0. In this case, same functions, however, it's going to be a growing sinusoid. Still exponential envelope, and the frequency of this is related to the parameter of the sinusoid. How about this? What happens to the real part of f of t and the imaginary part of f of t when alpha is 0? So when alpha is 0, we can write down a real part of f of t is going to become what? R, because alpha is 0, I shouldn't say alpha is, no, not alpha, should be a. When a is 0, so a greater than 0 is there, less than 0 is there. When a is 0, what is going to happen? Well, you're absolutely right. You're going to have an undamped sinusoid. So a real part of f of t is going to become r cosine theta plus bt. Imaginary part of f of t is going to become r sine theta plus bt. They are both sinusoids. They are undamped because the amplitude is not changing with respect to time. In other words, it is periodic. These were earlier, when alpha was not equal to 0, they were not periodic. However, now with a equal to 0, it's a periodic function. And if it's a periodic function, we should be able to find out the time period of this. So what is the time period of this function? Let's see. Time period will be related to the argument inside the cosine. So omega naught is what? Absolute of b. F naught will be absolute of b divided by 2 pi, which means the time period of this periodic function will be the reciprocal, 2 pi divided by the absolute of b. So if we know b, then we know, so b is right here. That is related to the time period of this periodic signal when a is 0. All right, so this is a little bit of a discussion on complex exponentials. There is a question in the chat box that I left for later. I will take a look at this question now. In the sine expression, is the a in the numerator of the exponential, or let's see. So that is a. Alpha was a plus jb. I'm not sure what in the sine expression. Yes, that is in the exponent. That is in the exponent, because that is in the exponent. A and t both are in the power of the exponent. So I guess I'm confused because there is no numerator here. There's no division happening. Okay, I'll come back to it if I left something unclear. Let me know through the chat box. All right, we talked about the complex exponential. Let's take a look at another way to classify signals by taking a look at their property of being even or odd signals. So signals could be even, signals could be odd, or signals could be neither. A signal x of t is called an even signal if it satisfies this property. X of t is the same as x of minus t, which means, x of 2 should be the same as x of minus 2. And for all t, actually, let me make that a part of the discussion. This is for all t. So no matter what the time, x of t should be equal to x of minus t. And if that condition is satisfied, then we can say that the signal is even. And you can quickly check that by taking one particular time, and this will help you probably think about this quickly. X of 2 should be equal to x of minus 2, x of 1 should be equal to x of minus 1, and so on. And it should satisfy for all the time, for all time. In other words, you can sketch the signal, and if it is symmetric about the vertical axis, it is even signal, such as the one that is shown over here. X of t is an even signal over here because what is to the right of the vertical axis is the same as to the left of the vertical axis. It is symmetric about the vertical axis over here. That indicates even symmetry. And we can test this by going in over here and say, all right, let's pick a point. Sometime, is it the same as when you, some t1, when you do a negative t1, you will be over here and it'll have the same amplitude. So those will be in line. So that particular definition will have to be satisfied for it to be considered as an even signal. Now, it may not be possible for you to sketch all these signals all the time. You could also comment on this by looking at the bracket notation. So let me erase these things so that we can go over the bracket notation for signal x of t. X of t is defined using a bracket notation in 4 different pieces. It is 0 for time less than -1. Note over here, I am ignoring any sort of discontinuity in the signal. So I'm not including -1, I'm not including 0, I'm not including 1. Place where there is a discontinuity, I am ignoring that. I'm not making it a part of my bracket notation. It's just so that the point over here is to be able to look at the bracket notation for classifying the signal as even or odd or neither. So let's take a look at this. 0 for time less than -1. Okay. And then between -1 and 0, x of t is a linear function with a slope of -1 and it passes through the origin, -t. Between 0 and 1, it is a linear function with a slope of 1 and passes through the origin, so t. And above 1, it is 0. Now, if you flip this around and say, okay, what is minus t? So you would have to replace all the t's with minus t in this. So let's start doing that. X of minus t for 0, well, that remains as is. You don't do anything over there. However, you change this. Actually, you just change this. Because instead of t, now it will be -t. Less than -1 will remain as is. And then when you multiply this inequality with a negative sign, you get what? T greater than 1. Next, -t will become t. -1 remains as is. T becomes -t. 0 remains as is. Multiply this inequality by -1. You get 0 less than t less than 1. Next, t becomes -t. 0 remains as is, t becomes -t, 1 becomes 1, multiplied by negative sign, -1, you get -1 less than t less than 0. Last one, 0 remains as is, t becomes -t, greater than 1 remains as is, flip multiplied by -1, you get t, sign change of greater than becomes less than, 1 becomes -1. Now try to match it up. So let me see. If you take a look at each one of those 4 pieces, you will realize that this is the same as that. This is the same as that, and so on. So all those 4 pieces of x of t match up exactly. So that's a bracket notation way to look at whether the signal is even or not. Symmetrical about vertical axis is one quick way to identify it. Next, how about odd signal? A signal is called an odd signal if x of t is the same as negative of x of minus t. So over here we are flipping things twice. One is about the x-axis and one about the y-axis. So when you flip on the y-axis, you have a negative inside the t, and when you do a flip on the amplitude, you get a -1 up front. So if the signal is symmetric about the origin, then it is considered to be an odd signal. For example, the one that is shown over here, it is symmetric about the origin, And we can go through a similar sort of analysis that we did earlier. We can express s of x of t in using bracket notation. It is 0 for time less than -1. It is t between -1 and 1. It is 0 greater than 1. And then when you write x of minus t, you get what? 0 for, two steps are happening at the same time. You are doing a negative t less than -1, and then when you multiply it by a negative sign, it turns to t greater than 1, and so on. And now when you match up these two, 0, -0, 0, -0, t, negative t. So x of t is the same as negative x of minus t. So same bracket notation, similar process, but now we have an additional minus sign up in the front, which means that it is flipping on both the axes, so symmetric about the origin. An interesting result for odd signals is that the area under the curve will be 0. So whatever you accumulate on the positive side over here will be lost or subtracted by the area accumulated over here, or vice versa, because it's symmetric about the y-axis. So you could have a negative area on the positive time, and then you could have a positive area on the negative time, but they will be the same, so they cancel out. Okay, let's so that's about classifying things into even and odd, classifying them based on symmetry, and sketch classifying them based on their bracket notations. Again, this is also for all time. Now, some properties about even and odd signals. If we are multiplying the signals x of t and y of t, and if you have a situation where x of t is even, y of t is even, both are even, then the product of those signals, which means essentially you are multiplying each time with each corresponding time in y of t, x of t1, y of t1, x of t2 multiplied by y of t2, and so on for all time. It's on a continuous basis. This property says if individually they are even, then the product of those two signals is also even. Similarly, if you have even x, odd y, then the product of those signals will be odd. If x of t is odd and y of t is odd, if both are odd, then the product of those two signals, continuous signals, is even. Let's go ahead and prove this middle identity. X of t is even, which means, so let's use this. Let's use x of t is even here, which means I can write that. And y of t is odd, which means I can write that statement. Y of t is equal to negative y of negative t. And then I'm going to define g of t, a new signal, which is defined as x of t multiplied by y of t. Instead of x of t, I will write x of minus t because it is even. Instead of y of t, I will write negative y of minus t because it is odd by definition. And I can pull that negative sign up front. I've got x of t multiplied by y of t, which is essentially how we defined g of t, because g of t is x of t multiplied by y of t. G of minus t should be x of minus t multiplied by y of minus t, so you get minus g of minus t. G of t, when it equals g of minus t, that means it is an odd signal. So the properties are like basic even odd math. Yes. And then, you can apply the same sort of methodology to prove the other identities. In fact, based on this, you could also prove these two things. Well, we'll talk about that in just a bit. Let's try to break these signals up into odd and even components. So a signal can be decomposed into its even and odd components. The even component of a signal, we are representing that as x sub e, the odd component of the signal we are representing as x sub o. The even component of x of t is defined as x of t plus x of minus t divided by 2. So there is a division, so there's a adjustment of amplitude, but we also need to do x of t and then add it to the x of minus t. For odd part of x of t, we do x of t minus x of minus t divided by 2. X of t is corresponding to the original signal here. So this x of t is the same as here, same as here, same as here. And then the flipped version, and you're flipping about the y-axis, you get that, and that. And you have to do also the divide by 2. Now you can quickly prove that it can be decomposed by just adding up the even and odd parts. When you add up these two parts, you get back x of t, because x of minus t will cancel out. So you get half of x there, half of x there, and then you get x of t back. So the claim is that you can decompose a signal into its even and odd parts or components by assuming. So you can by the way we have proved earlier a property, you can actually prove this property as well. Is even part of x of t actually even? Right, so you can look at the even part, which is right here, and to verify whether it is even or not, you can apply the property of it being even and check whether you get back the original signal. So similar steps, very similar steps. You're substituting x of t and x of minus t interchangeably and then verifying the property. And then similarly, you can ask a question over here: is odd part of x of t actually an odd signal? So for it to be odd, it has to satisfy the property x of t should equal minus x of minus t. All right, so that's as far as the decomposition of the signal goes. I think working with an example is very useful for this. So I have sketched out an arbitrary x of t over here, and a quick visual check tells me that it is neither an even signal nor an odd signal, because it's not symmetric about the vertical axis, it's not symmetric about the origin, so it's neither one of them. So I'm going to try to first find out what the odd component of x of t is, and my goal will be to sketch the odd component of x of t, and I'll also try to express it in the bracket notation. So odd component of x of t, let's work it out. Odd component of x of t is what? We have x of t minus x of minus t divided by 2, which means, let's see, I have x of t already. I need x of minus t. So for that, what I'll do is I will quickly sketch up that. So x of minus t is going to be what? It is going to be the flip about the y-axis. So I will have this guy over here. So this will flip to this and this. And then it'll be 0 afterwards, 0 there. And then let me just mark the important points. This is still 2, this is still 2, this is still -2, this is still 0, and this is still time. How about the y-axis? Y-axis is x of minus t. Right. And now I need to subtract them. When I subtract them, what do I have? Let's see. Let me write the equation over here. What is the equation for x of t between -2 and 0? It is a line increasing with a slope of 2 and has a y-intercept of 2. So it will be t plus 2. And it is simply 2 over there. Next, over here, what do you have? 2 here. It's fine. Over here, it is a line that is going down with a slope of -1 and a y-intercept of 2. So negative 2 plus t. Now what we can do this a little bit easier now. So let's try to sketch it first. When you sketch the odd component, what do you have? 2 t plus 2 subtracted by 2, what do you have? You have t. You divide by 2, what do you have? T over 2. So it is going to be t over 2 between negative 2 and 0. So let's see, negative 2 and 0 is going to be t over 2. And how about on the positive side? 2 minus negative t plus 2. What is that? And then divide by 2 as well. So it is also t over 2. So this will continue essentially. Let's see. Come on. Better. Beyond 2 and beyond negative 2 on either side, it is all 0. So that doesn't change. It will be 0 there. It will be 0 there. That is 0. That is 2. That is negative 2. That is what? XO of t. So that's the odd component of x. X-axis is time. What else do we need? Oh, we can mark the labels here. What is that guy and what is that guy? We know that it was t over 2. The line was t over 2. So if the x is going to 2, the y goes up to 1 and negative 1. And using this, you can clearly write that in the bracket notation form quickly as well. Let me erase this work here. Let me move this over there and express this in a bracket notation. XO of t is, I can write t over 2 between negative 2, t 2, 0 otherwise. And now if you take a look at this, it is symmetric about the origin. So it is satisfying our check for odd signals that it is symmetric about the origin. All right, so I hope that this was helpful. Now we will move into signal operations. So this topic is so if you were looking at one of the topics that causes a lot of confusion among students, and it remains for a long time as a potential confusion, signal operations. There are 3 signal operations that we are going to talk about. This tends to be very confusing, so I would encourage you guys to pay very close attention to these 3 operations. They are very simple, but yet they can be very confusing. So the first signal operation that we are going to talk about is time shifting. So a signal over here, x of t, can be delayed or be advanced in time. So when it gets delayed or advanced in time, just imagine this x of t signal moving left or right on the x-axis, along the x-axis, such as this. Right now, we have just assumed that it is moving right by some time tau. So we have done a time shift by that amount of time tau. So instead of 0, whatever happens at 0 is now happening at tau. Whatever was happening at cap t is now happening at t, cap t plus tau, and so on. So y of t is essentially expressed as the time shifted version of x of t. Y of t is the time shifted version of x of t. Now, clearly, that particular number tau, that particular variable tau, could be positive, could be negative. If it is 0, then that means that there is no time shift. But it could be positive, it could be negative, which means that we could have a delay or we could have an advance, which means that signal could move to the right of the original signal or to the left of the original signal. Now, before we actually go through the two steps, I want to point out this. One quick check that I would recommend you guys to do is this. To validate whether you have sketched things correctly or not, substitute, say, tau over here. What do you get? So when you substitute tau, you get what? Tau minus tau, y of tau. What do you have? X of 0. So this, I don't know if it is very visible here, but this is my tau. So y of tau should be x of 0. Is that the case? Y of tau is right here. X of 0 is right there. They are exactly the same point. So by substituting some quick numbers, you can check whether you are on the right track or not. Time shift talks about both possibilities, to the left or to the right. And that's the general case. Now we'll talk about the specific cases. When tau is greater than 0, then you have x of t minus 4, t minus 5, t minus 10, something positive, something greater than 0. That corresponds to the delay in the signal. Graphically, that means that the signal will shift to the right, exactly the same way as it is sketched over here by tau. When tau is less than 0, that means that the signal is being advanced. So whatever happens at 0 will now happen at a time before 0, -1, -2, and so on. That will be indicated still as x of t minus tau. However, in this case, tau will be negative. So that means you get something like t plus 4 and so on, t plus 1 and so on. In that case, the signal is actually shifting to the left by tau. So time shifting, in general case, and the two cases of delay and advance. Delay corresponding to tau greater than 0 and things moving to the right. Advance corresponding to tau less than 0 and things moving to the left. All right, so that's one signal operation. Next, let us go through this exercise. There are 3 exercises over here. Let us work through them. Sketch g of t. G of t is the gate function. Another common signal, gate function. And g of t is written up as u of t minus u of t minus 1. Let us sketch both of them at once here. What is u of t? Let us sketch that in red. U of t is 0 for time less than 0, then it jumps to 1 and it stays 1. Okay. Next, u of t minus 1. As you can see, I need to do a flip in the amplitude, and I also need to do a delay of 1. So things should be moving right by 1 time unit. So let's do that. Okay. And there. And then it is, 0 over there, and so on. And then, of course, this is going to be 1, 1, -1. This is 0. This is time. This guy is u of t, and this guy is u of, not u, negative u of t minus 1. Now, because I incorporated the negative sign already, when I do the subtraction, I get the gate function. What do I have? I have, let's see, g of t will be that. the gate opens at 0 and the gate closes at 1. The gate opens at 0, the gate closes at 1. T minus 0, t minus 1. The amplitude is also 1. This is time, this is g of t. I hope that example is clear. Next, we will try to express x of t is our arbitrary signal over here. We will try to express it in the form of g of t. We already know what g of t is. Gate function is a rectangular pulse that is on for 1 second with an amplitude of 1. That's g of t. So how can I express x of t? We can do this quickly. So for this, let me do this in red, let me do this in blue, and then I can say x of t. In red, I should say g of t minus g of t minus 1. The gate function is being flipped about the horizontal axis. That's why the negative sign. And then it is also getting delayed or moved to the right by 1 time unit. So that's why there you have a minus 1. So x of t can be written as g of t minus g of t minus 1. I've color coded it for clarity. Next, the last example over here is write x of t in terms of u of t. All right, so let's do that. X of t can be written as g of t minus g of t minus 1 in this set of examples. We have done that just a bit ago. G of t is actually u of t minus u of t minus 1. Open the gate at 0, close the gate at 1. Minus, you have g of t minus 1. What is g of t minus 1? Instead of u of t, you write t minus 1. Minus sign will now turn to a positive sign. G of t minus 1 will become u of t minus 2. What do you have now? Combine the terms to write the final answer. U of t remains as is, minus 2 u of t minus 1 plus u of t minus 2. All right, so I hope those examples were helpful in expressing one function in the form of the other. Next, we will try to do some sketching exercise with the ramp functions. We have 3 ramp functions over here, and we have been delaying some things and so on. So let's try to sketch them individually. Then we can work on drawing the final sketch. So let's see. I'm going to use red for the first piece. I will use blue for the second piece. And then maybe I will use pink for the last piece. Maybe not. Sure. Green for the last piece. Red. What is going to happen with red? R of t plus 1. So ramp, that means increasing with a slope of 1, but it starts at negative 1 because it has been advanced by 1 time unit. So it is going to go up starting from negative 1. With a slope of 1. Next, negative 2, so the slope is negative 2 r of t, so starting at 0. And it keeps going. And let's see, the last piece is going to be r of t minus 1. So from 1, it is going to go up because it's now delayed by one time unit. So those three pieces have been sketched together. Let's do this now. This is time. This is, well, you guys know what those are. This is also 1. Now, if you add all of them up, for time that is less than -1, what do we have? Time less than -1, there is absolutely nothing at all. So 0. Actually, I should probably stop here. Oh, come on. Next, between -1 and 0, what do we have? We only have something that goes up with a slope of 1. Between -1 and 0. Between, let's see here, this is 1, this is 0, and so on. Okay. Between 0 and 1, there is one guy that is going up by 1. There is one guy that is going down by -2. The slope is -2. So the result is going to be going down by 1. What happens after 1? Time greater than 1, you have two guys that are increasing with a slope of 1, one guy that is decreasing with a slope of 2. That means they will cancel out and you have nothing there. This is going to be your x of t. That is going to be 1, 0, 1, -1. So a triangle looking waveform. All right, I hope that was helpful as well. Let's look at the time here. Okay, we have a couple more minutes. Let's talk about the next signal operation, which is time reversal or time flip. We have been talking about this informally when we were talking about even signals and odd signals. Let's deal with that a little bit more formally now. The time reversal or time flip operation is essentially a flip about the y-axis. It can go from positive to negative or it can go the other way, that's fine. Either way, it is flip about the vertical axis or a mirror operation about the vertical axis. X of t is one waveform that is shown over here. Y of t is the time flipped version of x of t. So when you flip it, it flips about the y-axis. 1 becomes -1, 3 becomes -3, 2 remains as is. So it is just flip about the vertical axis. And in representation, what do you have? X of y of t is x of minus t. And again, you can quickly check these things. So for example, if I wanted to check whether I'm on the right track or not, I would say, okay, is y of 2, what is happening at y of -2? Well, you will see that it is y of -2 is x of 2. Is it x of 2? Oh, it looks right. So by using a quick check, you can validate your work, and I would highly recommend this for signal operations. So that's time flip. Now let's ask a very, very, very important question, which leads to the confusion that I mentioned earlier. What about the order of these operations? Let's take a look at what happens when you delay and then flip, which means you're doing the time shift first and then time flip. And then in the second case, we will take a look at flip, then delay. So when you delay first and then flip, y of t is the delayed version of x of t minus tau. So it's being delayed by tau. It is shifted by tau, but tau is positive, so it's a delay. And then once you delay, then we are flipping. So z of t is the flipped version of y of t. So delay, then flip. Now, how can I express z in terms of x? z equals y of negative t, y of negative t should equal x of negative t negative tau, right there. So only the negative sign applies for t, that's it. So when you do delay then flip, you get x z of t as x of minus t minus tau. Now let's reverse those operations. Flip then delay. Y of t is first getting flipped. So y of t is the flipped version of x of t. Z of t is the delayed version of y of t. So z of t can be written as y of t minus tau. Y of t minus tau can be written as x of minus, inside the parentheses you get t minus tau, which turns out to be negative t plus tau. And as you can see here, these are both different, meaning the order of the operations matter. Now, many students get confused about this. Which should I do first? Well, I can recommend one of them. I will recommend later on that you delay first and then flip. However, if you would like to first flip things, then in order for things to be equal, you will have to advance them instead of delay them. As long as you are able to keep track of that, you can do the operations in any order. But just so that there is a structure to the order of operations, you can do the delay first and then the flip. Right. Okay, so that's where we are. I can go one more step with the scaling operation. I hope you guys can give me a couple of minutes that we lost because of the technical issues here. Please bear with me for a few more minutes. The third signal operation is the time scaling operation. Y of t is represented as a time scaled version of x of t. In this case, you have x of alpha t, where alpha is a positive number. Alpha can be greater than 1, alpha can be less than 1. Well, if alpha is negative, then we go back to that time reversal situation. So we are kind of focusing only on alpha positive so that we talk about time scaling separate from time flipping, which we have already addressed in the second signal operation. So when alpha is greater than 1, it corresponds to a time shrinking operation, which means that the signal will shrink as suggested over here in this graph. When alpha is less than 1, it corresponds to a time expanding operation, which is indicated by a time expansion. There's a signal expanding in time as suggested by the green graph over here. Let's take a look at an example. X of t is, just so that we can do this, x of t is what? Open the gate at 1 and close the gate at 2. I've quickly expressed x of t in terms of unit steps. It was unnecessary for this example, but I just wanted to throw it out there. Let's see, x of t is defined as a pulse that starts at 1 and ends at 2 with an amplitude of 1. Now, if you do a time shrink operation or a time expand operation on x of t, how does it look like? So y of t, which is the time shrink version of x of t, is x of 2t. In this case, alpha is greater than 1. So what happens? It shrinks by a factor of 2. How do we know that? Plug in some numbers. So let's say I plug in I want to find out what is y of half. What is that? X of 2 times half, which is what? X of 1. X of 1 is the discontinuity with going up from 0 to 1. That's exactly corresponding with what I have for y. Similarly, you can do for any time. And I would recommend that you do keep track of that check. How about for time expand? Y of t over here in this example is x of t divided by 2. So alpha in this case is less than 1, it is 0.5. Still positive. Over here, things will expand. So 1 will now become 2, 2 will become 4. So the signal itself has expanded. The width of the pulse was 1 here, the width of the pulse over here is 2. So that's a time scaling signal operation. Now we can put all of these three operations together and come up with a full set of signal operation sequence. So when you do the combined operations of time shifting, time scaling, and time flipping, the recommended set of sequence is this: do the time shifting first, do the time scaling next, and do the time flipping last. So y of t is the shifted version of x of t, t minus tau. Z of t is the scaled version of y of t, y of alpha t. Alpha, again, positive number greater than, it's greater than 0. Flipped version of z of t is defined as w of t. So w of t is z of minus t. So if you put all of these three functions together, you have w of t, which is z of minus t. Z of minus t is y of negative alpha t. Y of negative alpha t is x of minus alpha t minus tau. So if you have a function in this form, all you have to do is plug in those three operations in that form: shift, then scale, then flip. Now, this will be the last example that we will work out today, which is to sketch w of t, which is the time shifted, scaled, and flipped version of x of t. X of t is given to us over here. It's the same ramp functions example that we did earlier. So what do I do first? I need to first do a delay. Why do I do a delay? Because it is minus 1. So delay by 1 time unit. Delay by 1 time unit. So delay means what? Shifting things to the right. Okay, so it becomes that. This guy is going to become 2, this guy is going to become 1, this guy is going to be 0. So that's the first step, delay by 1 time unit. Next, what is the second step? The second step is to do the scaling. What are we doing scaling wise? We are doing 2. So alpha is greater than 1. When alpha is greater than 1, what do we have? Time shrinking. Shrink or compress, however you want to think about this. Shrink by factor of 2. So this now becomes what? 0 remains 0, 2 will become 1, so it will become like that. The amplitude will remain as is. I've essentially compressed it, just compressed it. The third step is going to be what? Is going to be to flip it. Do I need to flip it? Yes, there is a minus sign there. About the y-axis. So sketch, sketch, flip. This is actually our answer here. This is going to be w of t, which is x of minus 2 t minus 1. This is 0. This will be negative what? Let's see, negative 1 half, negative half, and then this will be negative 1. That's it. All right. So that's a quick example on the three combined set of operations. Let's see, there have been some questions on the chat box. I will address those. The alpha doesn't distribute to, so the reason is alpha t, right? So instead of t, we are doing a substitution. Alpha t, alpha t, alpha t. The tau is after you have done the alpha. Right. So that's what I meant. But you see, if you choose to change the operations, what ends up happening is simply this: if you choose to shift later, you will have to do the reverse shift. So delay will become advance, advance will become delay. So if you do it first, then you can go through this step in that same sequence. Okay, so no, t and tau are independent variables. T is the time axis, tau is the constant. So all we are doing is changing the t. Tau is 4, 5, 6. It's not a variable. It's just it's the time shift amount. Yes. All right. So I hope this discussion was helpful. Um, and I hope you guys you know take good care of these combined operations. And I will assign homework problems later on in the day so that you guys can get good practice. Um, uh, 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 so there's a question on the chat box which says the slides prior to the lecture. Yes, absolutely. From next lecture onwards, I will be posting them ahead of time. The first two lectures happened in a very short duration of time, which is why I couldn't post them earlier than the lecture time. But from next week onwards, I will do that. No problem. All right. I'm going to stop recording at both places and maybe try to figure out which one worked.